Okay, in this video, we're going to talk about properties of exponents. We know that when we have a like base and it's raised to an exponent, that we can perform certain mathematical operations with those terms: adding, multiplying, raising to a power, or dividing. And I don't know about you, but I always try to find easy tricks to help me remember what the different rules are. So I've made up my own little saying to help me remember the rules for exponents. All night, my aunt ran mail downstairs. Kind of silly, but you can make up your own if you'd like. But what it helps me remember is the different rules depending on what mathematical operation I'm doing. When I add or subtract like bases with exponents, I really do nothing with the exponents. That means I can only combine like terms. I can only combine things that have the same exponent together. When I add and subtract, I do nothing. I just combine like terms. When I multiply things with exponents, I really add the exponents. Okay? When I raise something to another power, I really multiply. And when I divide like bases with exponents, I really subtract their exponents. Let's go through quickly and do a few examples of each. So on this first one, when I add or subtract like bases with exponents, I really do nothing with the exponents. I'm just gonna combine my like terms. So if I have 3x to the fourth plus 5x to the fourth, I can really combine those into an 8x to the fourth. I don't add the exponents, I do nothing with the exponents, I just combine my quantities together into one big 8x to the fourth. So for example, in this one, I have a 2y cubed minus a 1y cubed. Since they're like terms, they both have y cubes in them, I can take this quantity and subtract this quantity from it, and I end up getting a 1y cubed. I just combine like terms. If you look at our next example, it says we have a 4m to the fifth plus 2m squared. I have an m to the fifth here, I have an m to the second here. Since those are not the same quantity, they're not like terms, I can't combine them together. So I wouldn't be able to combine this into a 6. I would just have to leave them as separate terms with their own individual exponents. So I wouldn't be able to combine those at all. That's for adding and subtracting. We just combine like terms. We do nothing with the exponent. When I'm multiplying things with exponents, what we are really going to do is we're going to add the exponents together. As long as your bases are the same, we can take them and combine them into one term by adding their exponents. Think about this problem right here. We have a 2x times a 4x cubed. And we know that multiplication is commutative. It doesn't matter the order we do it in. And so if you really want to write this in a different order, I can say that I have a 2 times a 4 times an x cubed. And then I can combine my like terms here by multiplying my coefficients together. So 2 times 4 is 8. I have an x here. Really, I have an x to the first. I have one x. Here, I have 3 x's. So altogether, how many x's do I have? Well, I really have x to the fourth. I can also get that by adding their exponents together, 8x to the fourth. Another example, if I have 5w to the fourth times 3w to the fourth, I can multiply their coefficients together, and I can take this w to the fourth times this w to the fourth, and really I have how many w's? I have w to the eighth, or I can add their exponents together, as long as their bases are the same. On this next problem, our bases look a little bit different. Now, they're numbers instead of variables, and as long as my bases are the same, I should be able to combine all of them together into the same base. Here, I have a 2 cubed times a 2 to the eighth times a 2 to the first power. I have 3 2's here, I have 8 2's here, and I have 1 2 here. So how many 2's do I really have if I combine them? Well, I can add their exponents together, 8, 9, 10, 11, 12. I have 12 2's now. Okay? As long as their bases are the same, we can multiply by just adding their exponents together, keeping the base and adding their exponents. When I multiply, I really add. On the next rule, we're going to raise a power to another power. For example, if I have an x squared and then I want to cube it, what we really do with our exponents on this type of problem is we multiply them. If you think about it, on this example, we have an x squared, but we have 3 of them. So I have 1, 2, 3 x squareds. Really, how many x's do I have altogether? I really have 6 of them. So instead of writing them all out, I could quickly just multiply those exponents together. Okay? In this example, I have d to the fourth to the 4th power. That means I have 4 groups of 4. And so how many d's do I really have? Well, I have d to the 16th because I could just multiply them together. Okay? Same idea as if my base was a value, a number, instead of a variable. I have 3 3's and I have 2 groups of those 3 3's. So really, how many 3's do I have? Well, I have 6 of them because I can just multiply those exponents together. When I raise to a power, I can just multiply. The last one is if I'm dividing. If I'm dividing like bases and they have exponents, then I can really just subtract their exponents. If you think about this problem here, we have x to the 5th divided by x to the 3rd. What this really means on top is that I have 5 x's. On the denominator, I really have 3 x's. If they're just being multiplied together, then I should be able to reduce an x from the top and an x on the bottom. I should be able to reduce another one, and I should be able to reduce a 3rd one because I can reduce factors from the numerator and denominator. So then how many x's do I have left? Well, I really have 2 of them, x squared. Instead of writing all of that out, we can see that I can just take these 2 exponents and subtract them. So look at this next one. Instead of writing out 27 z's and 17 z's, as long as these bases are the same, I should be able to combine them by subtracting the exponents. So 27 minus 17, I would have a total of 10 z's. Okay. The last one, again, if we give you a base that is not a variable, so I have 7 to the 10th, that means I have 10 sevens. I have 7 to the 4th, I have 4 sevens. Think about how many sevens I would have if I were to reduce the numerator with the denominator. Or I can keep the base the same and just subtract the exponents. So what is 10 minus 4? I would end up with 6 sevens. Be careful not to reduce your sevens. They come together as one base and you have 6 sevens left over, not 6 ones. So be careful with that one. Okay? All night, my aunt ran mail downstairs. When I add and subtract, I do nothing. Combine like terms. When I multiply, I really add. When I raise to the power, I multiply the exponents. And when I divide, I really subtract the exponents. I hope that helps.